Hey, here, Mr. Saram speaks, and this is our philosophy of science video for gifted learners in this channel, Aristotle Learning. Today we'll talk on from MIT and Harvard, Manning et al. Work for automatically generating and testing social scientific hypotheses that published at 19 April 2024, about 1 week ago. Let's begin. Firstly, in silico means like in biology in vitro concept for automated social science. To carry out the automated social science had to develop a system that closely emulates the experimental process in real social science. The general steps involved are as follows. Firstly, social scientists begin by selecting a topic or field of study such as misinformation, auctions, bargaining, etc. Two, within this field, they identify interesting outcomes and potential causes that may influence these outcomes. These variables and their proposed relationships form the hypothesis. Third, they design an experiment to test this hypothesis by introducing variations in the causes and measuring the outcomes. Fourth, once the experiment is designed, social science create a pre-analysis plan to outline how they will analyze the data. Fifth, they then recruit the participants conduct the experiment and gather the data. Sixth, finally, they analyze the data according to the pre-analysis plan to estimate the relationships between the proposed causes and outcomes. In here, structural causal models, SCMs, play a crucial role in designing the system because they enable clear and unambiguous causal statements. This clarity facilitates precise estimation, and experimental design. Algorithms can determine exactly which variables need to be externally manipulated to identify the impact of a specific cause. If the initial two steps in the social scientific process involve constructing the SCM, the subsequent four steps can be directly determined based on the SCM. The system developed in Python and utilizing GPT-4 for all large language model queries allows for editable decisions at each stage. It takes as input various scenarios of social scientific interest, such as negotiations, bail decisions, job interviews, auctions, and more and more and more. Here's how the system operates. It starts with the given input scenario. Secondly, the system generates the outcomes of interest and identifies their potential causes. Third, agents are created varying along the exogenous dimensions of these causes. An experiment is designed. Fourthly. Fifthly, the experiment is executed using LLM-powered agents that simulate human behavior. Sixth, the agents are surveyed to measure the outcomes. And seven, and finally, the results of the experiment are analyzed to evaluate the hypothesis, providing insights for planning a follow-up experiment. Now we will talk on experimental scenarios, some experimental scenarios. First, A. Bargaining over a mark. Here is a scenario where two people negotiate over a mark was simulated. The system autonomously selected a buyer and seller as the relevant agents and identified the outcome as whether a deal occurs. Potential causes included the buyer's budget, the seller's minimum acceptable price, and the seller's emotional attachment to the mark. The system generated information about the structural causal model and experimental design. It automatically operationalized exogenous variables, the buyer's budget in dollars, the seller's minimum acceptable price in dollars, and the seller's emotional attachment on an ordinal scale. The simulation involved 405 experimental runs of the bargaining conversation between the buyer and seller. The fitted SCM indicated that all three causes significantly affected the probability of a deal. Firstly, a $1 increase in the buyer's budget led to a 3.7 percentage point increase in the probability of a deal. Secondly, a $1 increase in the seller's minimum acceptable price resulted in a 3.5 percentage point decrease in the probability of a deal. Thirdly, and finally, a 1 unit increase in the seller's emotional attachment to the mark led to a 2.5 percentage point decrease in the probability of a deal. Seemingly in the table, statistically significant paths are marked in red. Each path is given with its estimated coefficient and standard error in parentheses. The outcome is also given with its mean and variance. And finally, focusing, simple linear model equation is also important to calculate whether deal occurs. Secondly, a bail bearing. A scenario where a judge is setting bail for a criminal defendant who committed $50,000 in tax fraud was simulated. Secondly, the system selected the judge, defendant, defense attorney, and prosecutor as the relevant agents. Unlike the previous experiment, a more flexible interaction protocol was chosen, with the judge being the central agent and alternating with other agents. Judge, prosecutor, judge, defense attorney, judge, defendant, and so on. This protocol is referred to as the center-ordered interaction protocol. The system chooses the outcome as the final bail amount, with the proposed causes being the defendant's criminal history, the number of cases the judge had already heard that day, and the defendant's level of remorse. The defendant's criminal history was operationalized as the number of previous convictions, while the judge's case amount and the defendant's level of remorse were operationalized literally. In the fitted structural causal model, the following effects were observed. As defendant's criminal history, each additional conviction caused an average increase of $1,521.53 in bail. As defendant's level of remorse, the effect size was small but non-trivial with borderline significance. As interaction between judge's case count and defendant's remorse, this interaction was non-trivial. However, none of the other interactions or standalone causes had a significant effect, including the defendant's criminal history. Thirdly, interviewing for a job as a lawyer. In the third simulated experiment, the scenario, a person interviewing for a job as a lawyer was chosen. The system determined that the relevant agents were a job applicant and employer. Unlike previous simulations, manually selected the variables in structural causal model. The potential causes were the employer's hiring decision as the outcome and whether the applicant passed the bar. The interviewers' friendliness and the job applicants' hate. In the fitted structural causal model, only the applicant passing the bar had a significant causal effect on whether the applicant got the job. The effect size was substantial, with passing the bar increasing the probability of getting the job by 75 percentage points in a year. When testing for interactions, none were significant. And finally, an auction for a piece of art. In the final simulated scenario, three bidders participating in an auction for a piece of art starting at $50 was explored. Manually selected each bidder's maximum budget for the piece of art as the causes, and the outcome was the final price of the piece of art. Like the tax fraud scenario, the center-ordered interaction protocol was chosen for these simulations. The auctioneer was selected as the central agent, and the other agents were bidder 1, bidder 2, and bidder 3, who alternated with the auctioneer in that order. All three causal variables had a positive and statistically significant effect on the final price. A $1 increase in any bidder's budget caused a $0.35 and $0.29 and $0.31 increase, respectively, in the final price. For the piece of art for each respective bidder. These quantities make sense as each bidder has a 1 by 3 chance of being marginal. To exemplify LLM versus theory in this plot, the columns represent different reservation values for bidder 3 in a particular simulation, while the rows represent different reservation values for bidder 2. The y-axis represents the clearing price, and the x-axis lists bidder 1's reservation price. Black triangles track the observed clearing price in each simulated experiment. Also, the black line depicts predictions made by auction theory. The blue line in this plot represents the LLM's predictions without the fitted structural causal model, the predict yi task. The red line represents the LLM's predictions with the fitted SCM, the predict yi or beta I task. According to the plot, when provided with its suggested structural causal model for each scenario, the LLM can accurately predict the direction of estimated effects, but struggles to accurately predict their magnitude. The LLM's predictions for yi are scientifically less accurate compared to those generated by auction theory, which predicts that the clearing price will be the second highest valuation in an open ascending price auction with private values. Additionally, the LLM struggles to accurately predict the path estimates beta of the fitted structural causal model. Furthermore, investigated how the LLM performs on the predict yi task when provided with an SCM fit on all of the data except for the corresponding XY, the predict yi beta I task, while this additional information notably improves the LLM's predictions. They still fall short of the accuracy achieved by auction theory. As a result, the LLM's predictions are dramatically improved. if the model can condition on the fitted structural causal model. By assuming or searching causal structure in observational data, such as that generated from extensive open-ended simulations, there is a risk of misidentification. Structural causal models offer a solution to this problem by providing a framework that helps avoid misidentification. For assuming causal structure from data, the SCM-based approach eliminates the issue of poor contrast. Data generation relies on the causal structure, removing the need to instrument endogenous variables and assume their causal relationships. Exogenous variation is intentionally induced in the SCM to identify causal relationships in advance, even if being unsure how a new outcome fits into the causal structure. It can always assess its relationship with exogenous variables by fitting a simple linear model, seemingly in left diagram. A provides a correctly specified SCM from a randomized experiment, and B shows a misspecified SCM based on an assumed structure. For searching for causal structure in data, another strategy for identifying causal relationships when the underlying structure is unknown is to allow the data to determine the model. Algorithms can be used to find the model that best fits the data, but none of these algorithms can consistently identify the correct causal relationships from observational data. These algorithms take as input potential variables of interest, a graph with only nodes and no edges, and data for these variables, and they output a purpose directly acyclic graph or DAC that best fits the data. One simple algorithm generates all possible DACs for existing variables and then evaluates each model based on certain criteria. As an example, maximum likelihood, Bayesian information criterion, etc. And another method adds edges greatly to maximize the criteria, while penalizing the model for complexity based on additional criteria and removing edges until the model is optimized. This approach is now known as the greedy equivalence search (GES) algorithm. In some experiments, the GES algorithm incorrectly identified the causal structure. For example, in the tax fraud scenario, the algorithm identified the defendant's criminal history and the bail amount as the only variables with any causal relation. While this is partially correct, an increase in the defendant's previous convictions did lead to an increase in the average bail amount. The algorithm identified the causal relationship as equally likely in either direction. This highlights the problem of using algorithms without a correctly specified DAC. Researchers would have to make assumptions which can lead to inaccuracies. The SCM-based approach eliminates search problems because do not need to search for the causal structure given the data. Instead, generate the based on a proposed causal structure. Even if want to measure a new outcome using existing experimental data, have already identified the source of exogenous variation. Right diagram indicates that the GES algorithm incorrectly identified the causal structure. An approach to automated in silico hypothesis generation and testing enabled by structural causal models is demonstrated in this paper. The approach was implemented by building a computational system with large language models. Evidence is provided that simulations can elicit information from an LLM that was not available to the model beforehand. It is also shown that such simulations produce results highly consistent with theoretical predictions made by the relevant economic theory. These systems allow for controlled experimental simulations and masse with pre-specified plans for data collection and analysis, constructing, contrasting most academic social science research as currently practiced. Nearly frictionless communication and replication of experimental designs are facilitated, making replicability easier. Areas for future research include improving the fidelity of simulations by adding additional attributes to the agents, refining protocols for social interactions between LLM agents, determining optimal stopping rules for simulations, and setting up intelligently automated research programs for continuous experimentation. This is all of the Manning et al. Study from MIT and Harvard. Thanks for watching and give me a like. See you soon for future videos.